This is Unsiloed, brought to you by Alumni FM, connecting people through stories.
Hi, welcome to Unsiloed. This is Greg LeBlanc, and I'm here with Brian Christian, who is a visiting scholar at, is it a visiting scholar or fellow? Remind me, Brian, at UC Berkeley, working with human compatible AI and the Citrus Foundation, I believe. And he's also the author of this book here, The Alignment Problem, which I read recently. Fantastic book, Machine Learning and Human Values, and also the co-author of this book, which came out a few years back, called Algorithms to Live By, The Computer Science of Human Decisions. Welcome, Brian.
Thanks for having me.
So this book, The Alignment Problem, I mean, it's about the alignment between machine learning and human values. And kind of the way I thought about this book is, you know, there was a time when most artificial intelligence was kind of hard-coded and programmed by computer scientists. And then at some point they realized that it was a whole lot better if we could allow the artificial intelligence to learn kind of how to do what we instructed it to do, right? But we still would provide the robots or the machines with objective functions. We would tell them, okay, this is what we want you to do. And to this day, we still more or less tell them, hey, this is what we want you to do. And I think what you're asking is, you know, will there come a day where the machines will not just figure out how to accomplish goals, but will also kind of figure out what those goals are? And if that's the case, you know, then we need to think very carefully about exactly how they learn this. And maybe the way of learning objective functions needs to be a bit different from the way they learn, you know, how to achieve those objective functions. Is that a fair description of the book?
Yeah. I mean, I think in some ways, you know, what you're articulating is jumping to one of the solution attempts to the alignment problem. So maybe just by way of setting the stage, I'll step back for a second and kind of articulate the problem itself, just so we're, you know, on the same page. There has been this concern going back as far as 1960, you know, Norbert Wiener, MIT cyberneticist, around the field of AI, around the field of machine learning. And the way Norbert Wiener framed it was, you know, by way of an analogy to the sorcerer's apprentice, that we can think of AI as being like this kind of magical broom that we can enchant with these spells. But if we don't really know what we're doing, we're going to cast the spell that, you know, sends our system off the rails. And that's, of course, what the allegory of the sorcerer's apprentice is about. And Wiener says, you know, this is not the world of fairy tales. This is what's coming for us. You know, if we build these mechanical agencies, as he calls them, to do these things for us, then we had better be very careful at how we articulate what it is that we want them to do, their objective functions, as you say. And this was, I think, a pretty prescient fear for Norbert Wiener to be articulating that far back. And we have really seen in the last 5 years, I would say, these fears sort of coming to life. And we are now living in a world in which we no longer have to think about, you know, allegories for the alignment problem, but we are living in a world full of examples of that. Whether it is, you know, image recognition software that's captioning a selfie of 2 Black Americans as "quote unquote" gorillas, or it's, you know, potential disparities in the way that defendants are treated by risk assessment scores, or if it is, you know, self-driving cars that fail to identify jaywalking pedestrians and end up causing, you know, fatal collisions. So there are many, many ways in which we are already starting to see alignment problems in the wild. And this has a lot of people, I think, understandably concerned about what the path forward from that looks like. And so really the story that I set out to tell in the book is to profile the movement that we're now witnessing within the field of AI and machine learning, to address that and to figure out what are we going to do to make sure that these systems that we are, you know, increasingly entrusting with the running of parts of society as well as our own lives in a very direct way, how do we make sure that they do what we want? How do we make sure these learning systems are learning the right things? And so that, I think, has, in a very short period of time, gone from a relative taboo to becoming what, from my perspective, is really one of the most dynamic and most central parts of the field.
Yeah, and I don't think we need to go to Nick Bostrom's world where, the computers are all making paper clips, and stuffing the entire world with paper clips to see examples of these problems of misalignment. And you mentioned a few. And in fact, you start off your book with some of these well-known examples, which I think most people who teach in the world of machine learning will talk about. I mean, in my class, we talk about that, the gorilla example, and some of the other examples that you talk about. And I think that this is really fundamentally about a failure to specify the objective function in a way that aligns with what we. I mean, it's partially because we don't really know what we want, right? And so when we specify some objective, we think that's the objective that we're after, but then we find out over time that that's not a complete specification of the things that matter to us. And what I found really interesting in the book is how you kind of have made these parallels back and forth between kind of machine learning and human learning, and kind of machine decision-making and human decision-making, because the problems are the same, right? And so, how can we learn from human thinking and human learning when we're designing these machine learning methods, but also what can we learn from the machines about what it is that we're doing? So maybe we'll start by talking about, the problem at the beginning, which is really described by some as bias, right? And I think the word bias sounds attractive because it lines up with, both meanings of the word bias. But I think if we think about that gorilla problem, there might be some people who would say, well, this is not a bias. This is just the training data had, didn't really, the training data is the training data, and you're going to get, more accuracy with more data and less accuracy with less data. And this is the organic data that just existed out there in nature. And so, of course, it's behaving the same way humans would behave if they were exposed to this training data set. How is the algorithm supposed to know that we value these categories and that we want kind of equal accuracy across these categories and not across other categories?
Yeah, this is a great question. So there's a lot of different components, I think, to try to unpack here. And, you might have noticed that in the book, I rarely, if ever, use the word bias. And I think partly that's because it's so loaded not only with social meanings, but also with technical meanings, right? You have inductive biases, you have the bias variance trade-off. And so I tried largely to just kind of step around that particular term. But I think there's a couple things that are going on here, right? Well, there's one thing that's going on with training data where often what happens in academia as just this natural process of the field, people borrow each other's work. And so you can end up with a data set that's compiled. Like, to use an example, there's this data set called Labeled Faces in the Wild that was assembled at UMass Amherst in the late 2000s. And they created this by scraping newspaper articles off the web, which is very clever because the web has a huge repository of images, obviously. And crucially, newspaper images come with a caption, and the caption often identifies who's in the photo. And so this is really helpful if you're a researcher. You can start to ask, okay, can we identify whether two faces are the same person or not? And we'll use these captions to indicate whether the same people are in those photos or not.
I think you mentioned that they could probably recognize George W. Bush from any potential conceivable angle because his face appeared more than anyone else's, right?
Well, that's exactly it, right? So then your database comes to contain not a representative sample of, the human population, the American population, global population. It is representing the people who appeared in newspaper photographs. And so as, people who later went back and studied that data set found, there were twice as many images of George W. Bush as there were of all Black women combined, right? And so this is not the kind of data set from which you'd want to build any kind of actual commercial project that's going to affect real people. But there can sometimes be this issue that happens through no intended malice, but just this becomes the data set that more academics are using. So, it already exists. It's easier to use what's sitting around, or it's more advantageous if you're going to write a paper to use the data set that other people have been working from so you can benchmark things. All of that is just sort of par for the course in terms of the way that, academic science works. But then without too much scrutiny, some of these trained models can then get, reapplied in other cases. And then suddenly you find yourself in these weird situations where, you have a Black undergraduate student who's using this open source library and it doesn't detect her own face, so she can't complete her, student project. So things like that, I think, we do have to be a lot more careful about the data provenance and where these things really come from, because, if you're trying to build a face detector, you have to make sure you're not inadvertently building a George W. Bush detector. So I think that's one side of it. And there's more to be said there, and there's been a lot of work on that front, and so we can come back to that. But the other side of it is, as you're saying, also the objective function. So in image classification, the standard objective function is what's called cross-entropy loss, and cross-entropy loss implicitly expresses a constant penalty for miscategorizing any X as any Y. And, people like, for example, Stuart Russell, who you've spoken to, have made the argument that in practice, certain misclassifications are millions of times more harmful than others. But that's certainly not part of the objective function, which is treating every mistake as equal. So I think there's a lot of work to be done, both in terms of thinking about what are the data sets that we're really using, how do they generalize to the populations of people that are really going to be affected by a technology, and also how do we articulate what we are truly trying to get this system to do. If certain mistakes are many, many, many orders of magnitude more costly than others, we have to find some way of expressing that, or else by default, we're going to get a system that, doesn't do anything close to what we want.
Yeah. And I think that what's interesting about this is that there's no way to really figure out how to do it right from within the field of machine learning, right? I mean, there's no way that you can use purely statistical or machine learning techniques to identify whether you have chosen the right objective function, right? This has to come from outside of machine learning, right? So in business, when you teach data science, you say, listen, the only way to do model evaluation is to have some kind of, cost benefit matrix, right? So that you think carefully about the directionality of the misclassification, right? You have a cost benefit matrix that you attach to your confusion matrix or whatever. But that's when you have a clearly defined, profit maximization function. But if you have other objectives, this forces you to have to articulate them. And I think, you're saying that anytime you do this without making it explicit, you're essentially, advocating some implicit objective function. And you're endorsing the idea, for instance, that errors in both direction are equally important, because you're saying this model is better than that model. But how would we? So let's just use this example of, facial recognition. Suppose we say we want to have equal accuracy, across groups. Well, how do we decide which groups, right? I mean, if you're Google and you don't have, let's say you don't have any customers in China, then maybe you don't care if you're accurate in China, right? Because all you're trying to do is satisfy your customers. You're trying to minimize customer dissatisfaction. So if Google had 0 Black customers, then maybe they wouldn't care, right? How do we make sure that our training data set is is representative? Is it representative of what? Can we do this in any objective way, or do we have to sort of say, well, what is the objective function of Google? What is the objective function of the customers of Google?
Yeah, I mean, I think for one thing, it's tempting to some people to imagine that there are trade-offs here to be made. But I think what I've seen, if I look at the work of people like Joy Buolamwini from MIT, Timnit Gebru, who's worked at Microsoft and Google, they have shown that, many at the time, 2017, 2018, many commercial face detection, face categorization systems had error rates that were orders of magnitude greater for dark-skinned women than they were for, even relative to light-skinned women or dark-skinned men. That it was really the intersection of skin tone and gender that created these huge disparities. And what I was struck by after that research came out was that you had a response from some of the companies themselves that whose software was being critiqued. You had IBM, for example, within a matter of weeks, as I understand it, was able to internally verify Buolamwini's results. And if I'm remembering the timeline correctly, within something like 3 weeks, they had released a new version that was able to fix this issue without any really noticeable accuracy penalty in the other groups. Mm-hmm. And so I think we're far from the Pareto frontier in that it's not that IBM is having to make these trade-offs between accuracy with respect to different demographics of their customer base. I think my interpretation, at any rate, is that they simply weren't asking the right question. And once they started thinking about it, mm-hmm. they were able to find that they were far from the Pareto frontier and were able to just pick up this sort of low-hanging fruit, to pick up these wins without making any kind of accuracy trade-off or, financial trade-off. So I find that really encouraging. I mean, it's kind of a glass half full, glass half empty thing. It's discouraging that there were these, blind spots, but it's encouraging that it seemingly took no more than to just alert them to the existence of these gaps and that they were able to fix it. So, I take that as reasonably encouraging. But I think, to your point, if I'm understanding, where you're coming from, this is a case where there's no sort of obvious a priori mathematical function that's going to tell you whether these sorts of things exist. You have to kind of know to be asking the questions in the right way.
Yeah.
And so from that perspective, I think this is one case where, these are intrinsically interdisciplinary issues, that the methodology of social science in terms of framing what questions to be asking and ends up being kind of indispensable.
Yeah. I mean, we have to have, the social context. I mean, I think you made you showed an example where they actually used a data set that was much more kind of representative of the global population in terms of, say, skin tone and gender. But, that data set wasn't representative in a whole bunch of other characteristics, but those characteristics are not ones that, we might necessarily care about, right? And so inevitably it's going to be, for instance, differentially accurate for maybe people with eyeglasses or without eyeglasses, depending on, right, the proportion in the kind of training data set. The other example that I think you went into in some detail, which I found very interesting, was the parole mm-hmm. software, right? Which is being used pretty widely by a lot of jurisdictions, particularly here in the United States. And maybe you could kind of recount that controversy because, there again, there was no real, objective way to think about what's better or worse. But really, this is a case where there clearly were some trade-offs in terms of, different objective functions you can pursue.
So the use of statistical classifiers to think about things like probation, parole, pretrial detention, has almost a 100-year history in the United States. And I get into some of that in the book. And I think it's useful to have a little bit of that historical context in mind, because actually you discover that some of the arguments that were being made in newspapers of the time, in the 1930s, are eerily parallel to some of the things that people are saying today. Mm-hmm. So I think, there's a little bit of a sense in which, an awareness of history could prevent us from repeating it. But if you think about what's going on today, so there has been really an exponential increase in the number of states and jurisdictions using these statistical or algorithmic risk assessments, going from really, the 60s, 70s, 80s, 90s. And so really at the turn of the millennium, you have this phase transition where at this point, it's almost universal in the US that this is being used. And there's, I think, a warranted level of scrutiny and concern around, are these instruments, really accurate? Are they predicting what they claim to predict? Are there disparate impacts in the way that they affect different groups? And, there's an anecdote that I describe in the book where Minneapolis essentially rolls their own risk predictor in the 1990s, I want to say. And they make essentially a note to themselves to go back 12 months later and evaluate it, but they just forget. And they use the system for 15 years before they actually realize that it's never been validated. And when they run the study, they find that it's, there are several things that are being used as features in their model that have no predictive value at all, but they do correlate to race. So, they basically scrap the system overnight and start over. So that's the kind of thing where it is a little bit worrisome how some of these systems are deployed, citywide or statewide without an actual audit having been performed. So that is kind of a public oversight issue. But if you get into the actual kind of computer science side, you quickly reach this issue of how are we going to operationalize ideas that exist in, civil rights law, like fairness, disparate impact, et cetera. And this really came up in the context of a particular risk assessment system called COMPAS, which is used in many states, including New York, Florida, et cetera, et cetera. And there was a study that had come out from a team at ProPublica in 2016, suggesting that there, were apparently significant racial disparities in the way that the COMPAS scores were being assigned. This turned into a pretty big controversy, both in terms of public opinion, but also in the actual academic community of theoretical computer scientists. And people are asking, well, what do we mean when we say of a binary classifier that is quote unquote fair, with respect to one group relative to another? And it turns out there are a number of ways that you could try to operationalize fairness. The typical one, or the traditional one, is what's called calibration. So that says, if you have two defendants that are both rated, let's say an 8 out of 10 risk to be rearrested, they should in fact have the same probability of getting rearrested whether they're white or black. So another way of thinking about that is, an 8 out of 10 means the same thing regardless of who you are. And it turns out that COMPAS actually is calibrated in this way with respect to race. Ironically, it's not calibrated this way with respect to gender. So there's a separate conversation that could be had there. But what you did see in terms of the difference between black and white defendants was a difference in the actual kinds of errors that it was making. So if you look specifically at the defendants that were mispredicted, misclassified, you find that black defendants relative to white defendants are about 2 to 1 more likely to be misclassified as high risk white defendants the other way around, 2-to-1 more likely to have been misclassified as lower risk than they really were. And so you can say, both of these criteria seem very desirable, right? We want, the risk score to mean the same thing for defendants of, different races. We also want people who are essentially adversely affected by the mistakes that this model makes. We want them to, them to be essentially affected in similar ways, which they're not. And so you get a lot of interest from kind of the computer science part of this community, people like Alex Choldachova at Carnegie Mellon, John Kleinberg, Sendil Mullainathan, Manish Raghavan at Cornell and U of Chicago. And essentially, the punchline is you can't satisfy these two criteria at the same time. And so
it's kind of like it's kind of like an impossibility theorem, right? Where, there's multiple definitions of fairness, and you can't really achieve all of them unless there's sort of a constant base rate across these relevant categories. So there's,
right? There's computer science work to be done exploring the space of trade-offs that exist between those two criteria. There is work to be done, I think, at the interdisciplinary intersection between computer science and public policy around thinking about, which of those fairness criteria, if we can't satisfy them both, well, we have to make essentially a political choice of which one is the priority. I think if I step back a little bit, I see maybe an even more fundamental issue here than this, which is that we are fundamentally, this goes back to Norbert Wiener's critique, we're fundamentally unable to predict or even measure the thing that we actually care about, which is crime itself. Will someone recidivate or not? Well, we have no idea because no one measures crime. Like the vast majority of crime that gets committed is never known to the police. Many crimes, in fact, many, if not most crimes are never solved. Many people are wrongfully arrested. Many people are wrongfully convicted. And so we don't know the ground truth. We only know the arrest data and the conviction data.
Right.
And so in effect, we have built something that we often refer to as a recidivism predictor or a crime predictor, but is in reality an arrest predictor. And that's a meaningfully different thing. And I think that distinction is often elided, even by the people that use these tools.
No, I think that's a very important point. And I think that's, oftentimes we fail to very expressly articulate the kind of the thing on which we're supervising, right, in the model. Google famously came up with a model that was able to replicate the process of promotion, that they were using in-house. And of course, predicting that someone's going to get promoted doesn't mean that you're necessarily promoting the best people, right? It only means that you're promoting the best people if the system that you're automating was promoting the best people. And so we if we don't have some objective metric that we can use to kind of feedback through the system. And so this takes me to the idea that, we often forget that whenever we introduce a machine learning technique, it's there as an alternative to the human learning technique. And so it doesn't really matter how flawed it is. It matters how flawed it is relative to, what it's replacing. And so you offer a great anecdote about how in some jurisdictions, the predictive algorithm was telling the police officers to, say, pull over black drivers with a higher frequency than white drivers, but then they found violations at a much lower rate among the black drivers. And so, here's an example where the model could potentially learn, right? If it sees that there's this difference in the thing that it's supposed to be maximizing, it can then, feed that back into the recommendation and do so in a more systematic way than the humans do. So is the key to, a better model, making sure that you are carefully not only articulating the objective function, but designing these feedback loops, which rather than exacerbating the problem, can mitigate the problem.
I think this is critical. And I think, we're starting to see the field framing problems with regard to these long-term equilibria rather than, the nominal accuracy at the moment you deploy the system. Because once you deploy the system, then it is altering the very environment that is trying to predict. And there are cases where the model can self-correct, but there are other cases where actually it just sort of spirals out. So, one example that people like Moritz Hart at UC Berkeley use is lending, where let's say you have a population that has two different groups. There's a larger group and a smaller group. You have less data about the smaller group, just by definition. And so your model of who's creditworthy is going to be less good by definition. And so you deploy that model, you're giving loans to
higher default rate,
the wrong people, and then you observe what you think is a higher default rate, exactly. But it is not a property of the group, it's actually a property of your own model.
Exactly.
But the model doesn't know that. And so those are the sorts of scenarios that I think are quite dangerous. And I think there are subtler ways too, where, if you think about the Uber self-driving car that killed the pedestrian, Elaine Hertzberg in Tempe, Arizona in 2018. I read the National Transportation Safety Board report of that accident. It's quite revealing. I think there are many things that contributed to the accident, but one of them was the model appears not to have had any training data of jaywalkers. It looks like all of the labeled examples of people crossing the street were crossing at intersections or crosswalks. And so it was unprepared to encounter someone outside of that context. And B, it was using this classic object, categorization objective function where there were n categories. Something could either be a pedestrian or a cyclist or a car or a piece of debris. And it had this cross entropy loss for, misclassifying one thing as another. And yet this particular woman was walking a bicycle across the street. And so the logs show that this object classification system just kept flip-flopping. Oh, no, it's a cyclist. No, it's a pedestrian. No, it's a cyclist. No, it's a pedestrian. And so, fundamentally this classification task that was supporting the car's, braking system, the classification, ontology, if you will, was kind of brittle and unhelpful to the task. And bringing this back to your question about these feedback loops, I think there is a danger in cases like this where, we know from, George Box, the famous adage, all models are wrong, but some are useful. I think there's a danger in cases like this where the model can be wrong, but it can be wrong in a way that forces reality to meet the model where the model is, right? So the model doesn't understand what jaywalkers are. And so if you jaywalk, it'll kill you. And so people learn to stop jaywalking, and then the model stops being wrong because now there are no jaywalkers anymore. That's the kind of thing as well that I think we have to be really careful about. And so broadly speaking, I think there is very much this question of the model needs to somehow account for the fact that the model itself is part of the world that it's trying to understand. And I think that will be increasingly true.
Yeah, these feedback loops between, what the model is modeling and what, and the model itself are super important. You talk about the word2vec, right? Which I found fascinating, that story. Because it's not a new problem, right? It's a problem of, say, dictionaries in general, right? Should a dictionary contain an accurate description of how people use words, or should the dictionary offer, proper usage of the words, right? A dictionary is both sort of a positive and a normative institution. And so, when these kind of word recognition algorithms model the stereotypes and biases that we have, right? The more accurate it is, perhaps the worse it is, because it bakes in a lot of the things that we don't like about how we see the world.
Yes, I mean, unsupervised language models like Word2Vec, and of course now we're into the era of big transformers like BERT and GPT-3 and so forth. They're part of what makes them so fascinating to the computational linguistics community as well as to industry is this weird kind of universality or plasticity that you train this model, to do what's called, skip grams or bag of words. It's basically like a Mad Lib. It's learning to fill in missing words in sentences. But it just so happens that the internal representations that the model built in order to solve that task can be used for all sorts of things. You can use them for machine translation. You can use them to support, search relevance. And I think that's part of where we make this slide that you're describing between, the descriptive and the prescriptive, right? So if all I care about is identifying the missing word in a sentence, then you can understand why the model would, in a sense, quote unquote, want to know everything there is to know about human prejudice and human bias, because that's, if the corpora that it's training on have those biases, then that will help it pick the missing word in the sentence, assuming that the sentence has already been written by a biased human. All of a sudden, the rules feel different when you then deploy that model, and you use that to, think about the relevance of a particular resume to a particular job opening, or how you want to translate a passage from one language into another. Things like this, where we've changed the specification of what this model is supposed to do, but we've maybe not in a fundamental enough way rethought the assumptions of how the model was trained versus what are we actually going to deploy it to do. And so some of these prescriptive, descriptive issues that, as you point out, have been part of linguistics for centuries, really become salient in this context. And I think, the generality that these models have that makes them so exciting and so attractive can also be a big part of what makes them dangerous.
Right. And the other thing I found interesting was this idea that, the standard classic machine learning response to bias is, well, the great thing about machine learning is you can just delete the column that you're not supposed to look at, right? So if you're a bank and, under Fair Credit Reporting Act, you just say, well, let's just delete this, race column. Let's just delete this gender column. And then, problem solved. And, you use the example of, taking off the shoes for the blind audition, right? And you argue that the shoes are always there. You can always hear the shoes. And that maybe you actually have to keep that data in if you want to actually promote fairness. Sometimes taking the data out can, kind of make the problem invisible and make it difficult to remedy.
Yeah, this is a counterintuitive idea, I think, to a lot of people. But this is a foundational result in this literature. So there's a paper called Fairness Through Awareness by Cynthia Dwork at Harvard and others. And they really established this principle, which I think is yet to fully become absorbed by, let's say, the legal community or regulators. That sometimes you really, well, there's two things. One is that it's not sufficient, as you're pointing out, to simply delete this attribute. And the basic reason is that if that attribute correlates with other things, then it's going to be what's called redundantly encoded in the other variables anyway. So deleting it is not going to do enough. The second point is that it may be the case that only by having access to that variable can you correct for some of these things. So, this is just a hypothetical example, but let's say, in a particular state, you have data that suggests that, a black person is 3 times as likely as a white person to be arrested for marijuana, given some baseline same level of use of marijuana. right? Let's just say that that's the case. Well, you might imagine that the model wants to, in effect, treat a black person with 3 arrests as equivalent to a white person with 1 arrest. And so there, the race variable is mitigating the racial disparity that exists in the arrest record. So if you get rid of the race of the defendant and you only have the arrest record, then you don't have a way of, in effect, kind of balancing this disparity in how the variable that you do have access to was, generated. So there are examples like that, or, you imagine you're an employer, you're hiring, and you see that someone has, a 9-month gap in their employment history, and then you later learn that they were pregnant and they had took a maternity leave. Well, that might mitigate the otherwise negative impression left by this gap in the employment history. But if because of HIPAA or GDPR or, whatever, you are not allowed to know that the person was pregnant or had a child or whatever, then that can actually cause more harm than good. So there are examples like that. And so we're just starting to see articles, there's an article I cite in the book from the UPenn Law Review saying, for a long time, the legal community has viewed any use whatsoever of a protected attribute as a presumptive legal harm. But now, wait a minute, the computer science community is telling us both that, being blind to that attribute won't prevent these harms, and some of these harms are only fixable if we have access to that attribute. So maybe we over here in the legal community need to pay attention to what's going on in computer science and maybe rethink the way that we're approaching this problem.
Right. Well, in a couple examples in the book, you talk about kind of the principle of second best, which is something that economists love, right? And so, I think this would be an example of a second best situation where, in order to fix, one problem, you might have to do something that would normally not be desirable. But the bulk of your book is really about kind of reinforcement learning and, how reinforcement learning has really kind of augmented the tool set available to machine learning. But it creates a lot of interesting issues around learning in general. And so I think the way a lot of people think about reinforcement learning is they think about it in the context of, say, winning a game, right? And so if you win a game, then that counts as a reward. And then if you don't win the game, then you don't get a reward, right? Or and the problem with this generally is that there's not a whole heck of a lot of data, right? You have to do a lot of things, before you ultimately get this reward. And so, how do you actually learn how to win the game if you're not getting kind of intermediate rewards? And so a lot of what you're describing in the book is how do you kind of change the reward scheme so as to gradually scaffold the algorithm up to figuring out what it's supposed to do. And a lot of this comes from the science of educating people. How do machine learning experts learn from, say, psychologists? I mean, you read about Skinner and all these other kind of human behavioralists.
Yeah.
How much kind of flow of insight is there between these two disciplines?
Part of what I'm struck by is that I think there really is a dialogue that's happening between these two fields, and the insights are going in both directions. Mm-hmm. So, the field of reinforcement learning, I think, has some pretty deep-reaching roots into behaviorism, right? B.F. Skinner, as you mentioned, Edward Thorndike, the law of effect, this idea that he had at the end of the 19th century, I think he basically said, when you put an animal in a little box that it has to figure out how to get out or figure out how to get the food, it essentially behaves randomly. And then each of its random attempts is either, and his words were, satisfying or annoying. Mm-hmm. And he says, the satisfying impulses will be strengthened and the annoying impulses will be weakened. And if you kind of squint your eyes a little bit, that sounds an awful lot like epsilon greedy exploration. You try these random things, they get points, you do that more of the time. If they don't, then you kind of go back to more of a random strategy. So a lot of these ideas have a long history. Skinner in the middle of the 20th century was really interested in this question of what he called reward shaping. So if you want to incentivize an animal to do a particularly complex task, like his example was he wanted to teach a pigeon to bowl this miniature bowling ball and hit these tiny wooden pins. How do you actually incentivize that? You have to, his fundamental insight was you have to reward successive approximations to the final behavior. And so this is the idea of reward shaping, and that gets taken up by the robotics community, the reinforcement learning community in 70s, 80s, 90s. So part of what I find really fascinating is that once these ideas cross over into the computer science side, we can approach them with, I think, a deeper level of rigor. And so, there's a fundamental question that the reinforcement learning community was asking in the late 90s, early 2000s, which is, what is the class of alterations that we can make to a reward function that will leave the optimal behavior unchanged? We want to make the optimal policy more learnable, but we don't want to actually change it. I think that's a very deep problem. It has obvious connections to, reward shaping in animal behavior. It also has, I think, very clear connections to incentive design, in economics and management science. And so the computer science community is able to make some of these kind of foundational results showing things like, ultimately, to summarize kind of this technical result from Stuart Russell and Andrew Ng, what you really want to do is you want to reward states of the environment, not actions of the agent. And that ends up being this key, insight from the computer science side that I think has started to become appreciated by cognitive scientists and psychologists. So you have kind of this new generation of cognitive scientists, people like Tom Griffiths at Princeton, people like Falk Lieder at the Max Planck Institute in Germany, taking some of these ideas that the reinforcement learning community has discovered and saying, okay, now let's think about incentive design. How can we optimally incentivize people to complete a task or finish this, large project without, incentivizing them to do the wrong thing or to find some loophole? So I think that's just one example. And there are many. We can maybe get into this a little bit later in the conversation if you want, but there's a huge literature on intrinsic motivation in reinforcement learning that has everything to do with what we're learning about, infant cognition and how babies play and things like that. And it's both the case that, the reinforcement learning researchers at DeepMind are mining insights from the child psychology literature, but it's also the case that you have developmental psychologists like Alison Gopnik at Berkeley, Laura Schultz at MIT, borrowing these formal models of play from the reinforcement learning community and using them to model human behavior. So to me, that is one of the most, I think, exhilarating cross-disciplinary dialogues that's happening right now.
Yeah, I like this idea of curriculum for kind of learning, both for machines and for people, right? That you kind of have to coach them up in some ways. And one of the examples you use is if say an autonomous driving algorithm learns only from, really good drivers, then it doesn't really know what to do, right? When it makes a mistake, right? Because it finds itself in the ditch and it doesn't know how to get out of the ditch because there was no ditch in the training data, right? The car was never in the ditch, right? And so, I had a conversation with Dan Willingham a couple months ago, and he was talking about how, within the human learning literature, there's this misperception that you can teach people to read by having them imitate really, really good readers. But in fact, you want them to imitate, beginner readers, right? People who they're just like one step ahead of where you are. If you try to imitate the really good readers, you don't have that scaffolding. You don't have that kind of curriculum that will get you to where you want to go. And so you talk a lot about kind of gamification and how, when you put some of these algorithms in to the video games, sometimes they do really well, and sometimes they have a lot of trouble. And I'd never heard of this game, the Montezuma's Revenge.
Yes.
But apparently there's something unique about it that makes it very different from Super Mario. Maybe you could talk about that. I'm not a gamer, but
Sure.
I'm sure some people listening might understand both these games.
Yeah, well, Montezuma's Revenge is an old school game from the 1980s that was played for the Atari 2600. And yeah, to kind of frame it from the scientific perspective, there was a lot of interest at in academic research labs, and I'm thinking particularly of DeepMind here, circa 2013, 2015, at applying deep neural networks that had been so successful for things like image recognition into a reinforcement learning context, and trying to build these general agents that could learn to play not just a specific video game, but essentially any video game. And this led to the big Nature paper of Deep Q Networks 2015. But if you look closely at that Nature paper, you discover that, despite this model exhibiting superhuman performance at, dozens of different Atari games, if you scroll your eyes all the way down to the bottom of the graph, there's one game in particular at which the system scored a grand total of 0 points. And this is this game that you mentioned, Montezuma's Revenge. And the particular challenge with Montezuma's Revenge is what's known as sparse rewards. So it's a very unforgiving game. You're this explorer in a temple. The temple is filled with deadly traps. If you make one wrong move, you fall into a pit and die, or you crash into this enemy and die, or you get vaporized by this little, energy beam, or you fall into lava. I mean, it's just totally unforgiving. And you have to navigate this huge series of obstacles in order to reach this key object, which provides you the very first points of the game. And so this idea of random exploration, essentially let's just mash buttons until we get some kind of points, and then we'll back up and figure out what were we doing right? How can we do that more of the time? That approach works really well in a lot of games. In fact, almost all games, but it does not work in Montezuma's Revenge. The sequence of actions that you need to perform in order to get any points is so specific that the program, you're just waiting until, the heat death of the universe for the program to just stumble onto that sequence at random. Otherwise, it has no idea that it's on the right track. And so what do you do in a case like this? This is sometimes known as a hard exploration game, or as I said, a sort of a sparse rewards environment. The funny thing is that humans, of course, have no problem playing these games at all. So what's going on there? Well, part of it is that we kind of intrinsically understand that pixelated representations of keys are probably a good thing and a skull is probably a bad thing. So we have certain priors, like visual priors that we bring. But part of it is also we have this innate sense of making progress. Even if we're dying all the time, if we are able to get to a second room that we've never accessed before, we feel like we're doing something right. We have a certain curiosity to see what's behind the door, but we also have kind of this intrinsic reward where we feel like we've done something good, whether the game gives us points for having done that thing or not. And it turns out this is exactly what is required if you want to get reinforcement learning agents to play this game, is this kind of intrinsic reward that comes from merely seeing a novel image on the screen. And so what DeepMind researchers circa 2016 worked out is that you can plug in essentially a generative model that's assigning these probabilities to the image that's appearing on the screen. And if you treat the encountering of a low probability screen as a reward, and you essentially, splice that into the game's score mechanism so that the agent feels, just as reinforced when it encounters a new screen as it does when it actually, gets points from the game itself. Suddenly your agent is exploring in a way that shows what from the outside looks like this drive. It essentially wants to get to the next room just to see what's there, to, you know, open the door or cross the bridge, etc. And
you described this as kind of giving the agent curiosity,
yes,
right? Like injecting curiosity into the agent.
Yes, exactly right. And this is a case where, you know, you have people on the reinforcement learning side, like Mark Belmar at DeepMind, people like Deepak Pathak at Carnegie Mellon, very much looking over the disciplinary divide and thinking about formal models or theories, at the very least, of infant play. And, you know, one of the things that had been pretty well established in the cognitive science psychology side is that infants exhibit what's called preferential looking. So they just, you show them two things and they'd seen one before, they look at the other thing that's new. And so that was one idea of, okay, let's plug that into Montezuma's Revenge. We'll just add this little, you know, pleasure for seeing an image on the screen you've never seen before. And then more recent work has looked at the notion of surprise. So can the agent have kind of a model-based system that's predicting what it thinks it's going to do, and then anytime the agent is wrong about what it thought would happen, treat that as a reward and sort of reinforce that behavior because it enabled it to learn something about the dynamics of the environment. So as I say, I mean, I think that's really thrilling to me because as, you know, if you like, as machine learning, as AI becomes more human-like, suddenly we have all of these insights that are just sitting around, ready to be mined, you know, ready to be kind of summoned to the task. And at the same time, increasingly the cognitive scientists are able to go to the reinforcement learning literature for inspiration and ideas. So it really is going in both directions.
Yeah, that I found fascinating from the chapter on curiosity. You were talking about how we can learn a lot more about how we as humans learn from what's going on here. And in particular, when it comes to curiosity, you mentioned that there's this tug of war between, you know, on the one hand, curiosity is all about seeking surprises, but on the other hand, over time, we make ourselves more and more difficult to surprise by essentially compressing the data into a format that we can understand. And so you also make the point that there can be too much curiosity, right? If you over-reward curiosity, then the agent will just kind of, you know, get into this loop, which you kind of describe as addiction, right? So you can actually create an addicted agent, which will just keep, you know, seeking this novelty in an endless loop, right?
Yeah, I think it's recognizable, certainly. Like if you sort of anthropomorphize it, it's certainly recognizable as addiction behavior, right? And there are cases where, you know, different reinforcement learning agents will be essentially mesmerized by something stochastic in their environment because they'll keep trying to model it and, you know, become fixated on trying to predict this thing that's fundamentally unpredictable. And that, you know, if you kind of squint, that feels a little bit like, you know, the way people can become addicted to games of chance. It also it reminds me of why it is kind of hypnotic to look at a campfire or a waterfall or something where there's just this intrinsic visual noise that you can't quite, you know, predict no matter how long you look at it. And we've also seen agents that became essentially, you know, couch potatoes. There was a great study done by folks at Berkeley and OpenAI on agents that had this really strong kind of intrinsic novelty surprise drive. And if you put an actual, you know, image of a TV screen inside of this game environment, you know, it's trying to navigate its way through a maze, and suddenly it encounters like a television. And maybe it even has like a remote control where it can push buttons and change the image on the screen.
Yeah, it has to be a television that you can change the channel a lot, right?
And you know, why finish the maze when you can just sit there changing the channel, because it's so fascinating and unpredictable, and it's such a rich source of kind of visual novelty. And so I think, you know, in my view, these are more than analogous. I think, you know, there are many ways in which reinforcement learning has, in my view, shown itself to be brushing up against some of the kind of fundamental mechanisms of learning in animals. You know, there's a whole, you there's a whole dive that we could do into the dopamine system, the connection between that and temporal difference learning. But I think the takeaway is we really are starting to reach the beginnings of an understanding, a scientific understanding of how learning works in the brain. And this really is useful for, getting a framing for things, the good and the bad, right? Curiosity, play, exploration, but also, boredom, despair, addictive behavior, compulsive behavior.
Now, I think we're going to move to a world where, human decision-making and algorithmic decision-making are going to be taking place side by side. And, we're going to be working alongside, the robots, so to speak, or we're going to have working for us teams of humans and robots. I use the term robot, right? In a general sense. And so, how these two can complement one another is sort of where you end up the book. And you talk really about, what's it going to be like when we have so much more decision-making being done, by machines. And one thing that you mentioned about humans and how we differ from pretty much every other animal, is that, we're really good at inferring intent. We're really good at understanding what other humans are trying to do. And, you offer this fantastic, story, this example involving the boxes. And it basically says that, imitation, humans over imitate relative to other animals, right? And which seems to be stupid. It seems to be irrational. But you talk about how, this is actually what makes us human, this kind of over imitation. And furthermore, it reflects a very sophisticated theory of mind, because we only over imitate when we perceive some kind of intent, right? Mm-hmm. Could you walk us through that story?
Yeah.
And what it illustrates?
I think this is a wonderful example. So if you have a contraption, a box with different latches and things on it, you can have a human demonstrator show that, okay, I'm going to open this thing and then I'm going to go and open that thing and then there's some food in there.
And it's almost like an incantation, right? If a human says, okay, this is how you do it, you say abracadabra and then you open the box, right? Then, a learner is probably going to say abracadabra and then open the box, right?
Right. Yeah, that's right. So, part of where this gets interesting is they run it in two conditions. In one condition, the box is opaque. In the second condition, the box is transparent. And so you can actually see that the first half of what they're doing has no relevance whatsoever. You don't know that in the opaque condition, but in the transparent condition, you can tell that it's useless. What you find out is that if you do this demonstration to a chimpanzee, the chimpanzee will faithfully imitate both halves of the action in the opaque condition. But in the transparent condition, they just think you're an idiot and they'll only do the part that's, actually effective. Okay, that seems pretty intelligent. The funny part is that humans, 3-year-olds, for example, 3-year-olds, even when they can see that the first half of what you did doesn't do anything, they'll still imitate both the useless part and the useful part. And this was kind of a mystery. And people thought, okay, well, maybe it's just the case that humans, are slower to develop at, relative to a particular age. So let's swap out the 3-year-olds. Let's bring in 5-year-olds. The 5-year-olds were even worse. And so what the heck was going on? And if you ask the 5-year-olds, is this part silly or is this part necessary? They can tell you like, no, that's silly, but they'll still do it. And so for me, this is very fascinating because what it shows you is that the initial hypothesis is that the chimpanzee is smarter than the child because the chimpanzee can tell the difference between what's helpful and what's not, and only does the useful part. And that was the initial hypothesis. But actually, it turns out that no, the human children are one level of theory of mind above that. So the human children know full well that you've done something useless, but they also know that like you're the demonstrator, you're in this pedagogical mode. You are an adult that's even smarter than they are. And so there must be some reason that you're doing it because otherwise you wouldn't be doing it. Whereas the chimpanzee just thinks that you're an idiot. And so I think this is a really,
and I think you said the way they know that is that if for instance, you're not in demonstration mode, but if you're kind of, doing it, and you don't realize you're being, observed, then the children are more likely to ignore the first part, right?
Yeah. I mean, there are a number of different kind of twists on this, but the one experiment that for me kind of nails this is, if there's like a button on the table and the experimenter pushes the button with their nose, then the kid will be able to determine whether the person did that on purpose or whether like the person's arms were like tied up or holding something or da-da-da. They can tell whether you've pushed it with your nose out of convenience or whether you've gone out of your way to push it with your nose. And so they'll make the determination on that basis, and they'll either touch it with their hand if they saw that your hands were tied up, or they'll touch it with their nose if they can kind of infer that you've done it that way on purpose. So I love this story because it shows that underneath what seems like foolish behavior or kind of rote behavior, like the kid is overly imitating the adult, even the parts that are pointless. Actually, there's a much more sophisticated thing going on than we were initially assessing, which is that they're getting inside the head of the demonstrator and saying, okay, there must be I can see that this doesn't make sense to me, but they must be doing it for a reason. And so I'm not going to ask questions. I'm going to trust the authority. I'm going to trust the adult, which is, any time outside of a laboratory study is probably the right thing to do.
Now, I guess the reason why you include this in this chapter is because part of what I think we're ultimately looking for are agents that will understand what it is that we're looking for and act on our behalf, right? When we let Facebook decide what content we're going to read on a given day, right? We're putting a lot of trust in Facebook, and we're hoping that Facebook is giving us, what we want and not what someone else wants. We expect it to be a faithful agent. Designing a faithful agent that's a machine is certainly no easier than designing a faithful agent that is human, right? And actually figuring out ways to specify, when should we allow them to make decisions without our intervention, and when should they seek out our consultation when they're in doubt. This is a very, very difficult thing to articulate. And sometimes, we may even want them to override our preferences in the moment, right? Maybe sometimes they're acting paternalistically and, we want them to act paternalistically. So this seems to be one of the more fundamental problems that we're ultimately going to have to confront. I mean, we're already confronting it. And this is where you have to come up with some way for the agent to kind of, learn what the objective function ought to be. So will, machine learning ultimately become automated, sociology, automated, philosophy? Will we be able to, have kind of artificially intelligent social science and artificially intelligent ethics?
I think this is a really interesting question. So, part of what's going on here in the computer science community, which brings us back to kind of where we began our conversation, is this idea that, it's very, very difficult to hand specify an objective function that, somehow factors in everything that we care about, everything that we want. And so there's been a movement within the computer science community, and I think about people like Stuart Russell as being part of this, to move away from the world of manually specified objectives into a world where the objectives themselves are learned by this machine learning system. There's been a lot of really cool research, and from my view, frankly, encouraging research on this. My personal favorite is a paper between OpenAI and DeepMind where they were able to get a system to learn how to perform a backflip in this virtual world, merely by showing users pairs of video clips of it moving randomly and saying, which of these is slightly more like a backflip? And by showing people 900 such video clips and just saying, which of these is slightly more like a backflip? the system was able to infer a representation of what a backflip was, that was good enough for it to then learn how to execute these beautiful, gymnastically perfect backflips, sticking the landing, etc. And I think that, to me, is, frankly, is about as hopeful as I have felt about this problem space in many years, because I think there is this promise that we can develop a methodology for extracting somehow the norms, the preferences that we have in our head, right? You can think of a backflip as like an aesthetic preference that's very hard to articulate with code. It's very hard to articulate it verbally. It's hard to even demonstrate it for most of us. But we have developed a method for kind of distilling that information out of the brain of a person and getting that into a machine. So I think that's, it's not obvious to me that would have worked. And it was not obvious to the researchers on the project that it was going to work. So that's the kind of thing that I think paints a hopeful picture as we sort of move forward, that, it has always been the case, if you look at the commercial side of tech, that someone within the organization has this job of determining, like, what are the metrics for that quarter? Are we caring about, user churn? Are we caring about average revenue per user? Are we caring about customer satisfaction? Whatever it might be. Are we just caring about the maximum time on site? Whatever it might be. And people have meetings about what these metrics ought to be and so forth. There's a little bit of a sense that we're moving from that world into a world where the metrics to be optimized are themselves being selected in an automated way. And we've seen, research coming out of social media companies to this effect. I think there's something hopeful about that, but there's something, to be concerned as well, right? So if even the engineers at the companies themselves don't know really what their system is even trying to do, let alone doing, I think that's concerning. I think it's concerning from the perspective of, who are the people that get to decide, in effect, which thing looks more like a backflip, right? So you have the classical ethical conundrum of, who's the decider that decides which of these two worlds is a better world to live in. And then ultimately, for commercial tech, you have to ask the question of, how does the business model of the company fundamentally align with the interests of the users? To say nothing about this automated system that's mediating their relationship, but how aligned are the principles in this exchange to begin with? And that's, for me, that's kind of coming full circle on this question of the alignment problem. The term started in the economics literature, and in some ways we've come full circle, where if we can, quote unquote, solve the alignment problem from a technical perspective, such that we can get an automated system to be fully aligned with the desires of the people that are building it and operating it, you're still left with the question of, do those interests align with the people that are affected by the system? So, we're not out of the woods by any measure.
Yeah. And so to circle back to where we started, what Google did is they actually had a human manually delete gorilla as a category, right? So even if you have a photograph of a gorilla from the zoo, it's going to classify, I guess it just leaves it blank, right? It just says, not recognized. Okay. And so could there be a day when, that stake was cut off at the pass by some agent that is just simply reading the newspaper, and it understands from the newspaper that, hey, this is not a cool thing, right? This is going to be a big problem. And it could intervene and fix that classification, or at least, provoke a different kind of trading data set collection initiative. Do you think that day will come when the machines will kind of know ahead of time what sorts of things it
I
ought to
think
be doing?
There's hope that people have that, somehow we are going to develop an infrastructure for instilling all of the incredibly complex norms and values that people have in a kind of automatic way. I mean, so to use your example, right, just reading all of the internet and learning that, certain things, in this case, racial stereotypes that have this historical origin are harmful. I think, there's a number of steps along the way that I think of as kind of stepping stones in that direction, right? So, if fundamentally Google Photos made that mistake because of a paucity of training data of people that looked like the person who took the photograph, we're increasingly able to quantify a system's uncertainty. And so that might be the kind of fail-safe where the system says, actually, I don't really know what I'm talking about because I haven't seen enough stuff to feel confident. And I think, a more contemporary version of that system would just defer to make any judgment, or it would sort of flag that and send it to a human team for kind of review. So there are certain things there that we can kind of automate. In terms of, full-blown extraction of human norms out of language corpora, I mean, there are people that think we're going to get there. I'm a little bit agnostic. I'm also a little bit, of course, worried that a system that, extracts ethics from, Reddit and 4chan is the kind of thing that we want to just entrust with society.
Right. I don't think the current policies of Google and Facebook would have been derived from a comprehensive reading of the kinds of things that are on the internet. So I think you'd have to do some curation there. You end the book with a very provocative quote. You say that the danger that we're facing right now is not that of losing the world to AI, right? Losing control of the world to AI, but really it's about the danger of losing the world to models. What did you mean by that?
Yeah.
Of course, you quote George Box, right? I mean, is it danger of losing world to bad models, or is it the danger of losing world to useless models or models in general?
I think, this touches back on this issue that, all models are wrong. And so what do you do if you have a system that's operating with a flawed model, imperfect model? Off the bat, there's kind of three ways to address that situation. You can improve your model to more closely match reality. You can reshape reality to more closely match the model. And that's not always as nefarious as it sounds, like a thermostat, arguably like a feedback controller in a thermostat.
Yeah. Or a ring-fenced area for, autonomous vehicles.
It's not always nefarious, but it certainly can be. And that is one of the things that keeps people like myself up at night. And the third thing is to somehow operate informed by the knowledge that your model's imperfect. So I think what I mean when I'm saying this is not really an AI problem as such. I mean, if you think about the way that the world operates at the highest, most general level, we have somehow determined that there are various incentives or various KPIs that correlate generally with the world that we want, and those incentives exist in democracy. We generally think that winning elections requires you to do things that people want you to do. We generally, if you look at the stock market, right, we generally think that, shareholder value correlates with, selling products that help people. And those, objective functions, if you will, those operational definitions of what we're trying to do, again, at the most macro level as a society, they work until they don't. They correlate with human flourishing until they don't. And you see, I'm prepared to argue that many of the non-AI problems facing the world, things like, polarization, inequality, climate change, you can think of them as alignment problems. You can think of them as we're overfitting to these brittle metrics that capture certain aspects of what we want, but not everything. But we've just hit the gas way too hard on these particular metrics, and we're now, they've become decoupled, right, from these proxies that have become decoupled from the thing that we actually cared about. And so, the pessimist in me says, we're worried about these future scenarios of what might happen when AI is, like you mentioned the paperclip maximizer, right? We're worried about some hypothetical future scenario in which the AI gets this objective function that gets unglued from human flourishing. But I think you can argue fairly persuasively that we're already in that world, whether the things doing the optimization are corporations, nation states, or, machine learning systems is maybe less relevant than one might suppose. So, the optimistic view is that some of the work that's being done in the kind of nominal AI safety community actually might be applicable to these higher level problems as well. So that's with my most hopeful, attitude. I think maybe we can start to work ourselves out of what you might think of as the tyranny of these kind of narrow operational definitions of what it is that we're trying to do on this planet. But that's a long road. But I see a hopeful story, if we play our cards right.
And I think if that hopeful scenario is going to play out, I think we just need more communication between these different communities and more books like this one right here, The Alignment Problem, Machine Learning and Human Values. Brian, thanks so much for joining me.
It's been a pleasure. Thank you.
This is Unsiloed, brought to you by Alumni FM, connecting people through stories.
Person next time. There we go.